Yep.
Yes, so he will be speaking about MinerRay. This is about semantics-aware analysis for ever-evolving cryptojacking detection.
Yeah. Thanks, Julia. So, hi everyone. My name is Alan Romano. I'm a third-year PhD student from the University at Buffalo, and I'll be presenting MinerRay, a semantics-aware analysis for ever-evolving cryptojacking detection. This is joint work with Dr. Yunhui Zheng from the IBM TJ Watson Research Center and my PhD advisor, Dr. Weihang Wang from the University at Buffalo. I'll begin with a bit of background. First of all, what is cryptomining? Cryptomining is mining for cryptocurrencies by solving cryptographic puzzles referred to as proof-of-work algorithms. Proof of work usually involves finding some target hash that, when input into the algorithm, meets some criteria specified, such as ending in 4 zeros. By finding these values, miners get rewarded. Cryptojacking is cryptomining without the consent of the owner of the device. Specifically, we focus on in-browser cryptojacking, where an infected or malicious web page performs cryptomining in the background. This steals resources from the user to create money for the attacker, and these types of attacks have been going on since late 2017. Cryptojacking can cause widespread impacts, and an example is seen in July 2018, where an exploit in MikroTik routers allowed attackers to automatically inject CoinHive's mining scripts into all the pages that were sent back to connected devices. Initially, this affected 170,000 devices located within Brazil. By September of 2018, the number had grown to 280,000 devices and had spread worldwide. By December of 2018, the number had grown to 415,000. This example shows the need for detection techniques and showcases the severity of these types of attacks. In-browser cryptojacking attacks happen in these steps. First, a user visits the website with a JS miner and downloads the JS miner from the provider. The JS miner then opens a connection to the mining pool and sends a site key to authenticate the user, in this case, the attacker. When the mining pool authenticates the user, they assign a job to the miner. The mining script then begins computing the hash for this job, and this is usually done with WebAssembly because of its performance advantage. When the hash is computed, the result is submitted to the mining pool, where it verifies the hash, and if it's valid, it sends a new job to the miner to perform. This process is then repeated. Now I'll give some definitions of some terms that we'll use. Cryptocurrency is a virtual currency that uses blockchain technology to record its transactions. The Cryptomining Services are the actual providers of the mining script code and the ones that manage the mining pool. Proof-of-work algorithms provide consensus for a decentralized system and require significant computing power. These usually involve some kind of hashing function. One of the most popular targeted cryptocurrencies in these cryptojacking attacks is Monero. It's provided by popular services such as CoinHive, CoinImp, Omine, and more. It uses the Cryptomining algorithm in its proof of work, which is a memory hard algorithm that uses AES rounds and Keccak, Blake, Grossel, JH, and Skyne hashing functions. There are various related works on cryptojacking detection, but they have their limitations. Some detectors, such as Minesweeper, only focus on detecting one algorithm, usually kryptonite. Second, some detectors, such as MinerBlock and NoCoin, focus on signature functions or predefined runtime behaviors and can detect new currencies that don't follow these. Third, several techniques expect a WebAssembly component when scanning, and they can't detect miners that are either implemented entirely in JavaScript or hybrid miners implementing core components in both WebAssembly and JavaScript. Another popular targeted cryptocurrency is Uplexa, and it uses the Kryptonite UPX variant of the Kryptonite algorithm. This variant focuses on mining in low-power embedded devices by reducing its processor and memory runtime usage. This can throw off detectors that are tuned to Cryptonite standard algorithm. Another targeted cryptocurrency is JSE coin, which uses the SHA-256 lottery system as its proof of work. And this is very different from Cryptonite. In addition, it's implemented in JavaScript only, which throws off detectors that expect a WebAssembly component. WebDollar is another targeted cryptocurrency that uses Argon2 hashing within its proof of work. It's implemented as a hybrid miner in JavaScript and WebAssembly, with JavaScript managing the hashing iterations and WebAssembly performing the actual hashing function. This hybrid implementation allows it to hide from detectors that only search one language at a time. These examples show an increasing diversity of in-browser crypto mining implementations. And for this reason, we developed MinerRay, a semantics-aware analysis for ever-evolving cryptojacking detection. Our technique is resilient to variations in hashing algorithms and can detect miners implemented in either JavaScript, WebAssembly, or hybrid implementations. We do this by proposing an intermediate representation to abstract the underlying hashing semantics in WebAssembly and JavaScript. Hashing functions are an important primitive in proof-of-work algorithms. These functions map some input of arbitrary length to a fixed length output. Ideally, this output is fairly unique to the given input. Almost all cryptographic hashing functions are based on block ciphers and operate on the message in an iterative manner. Generally, hashing functions have 5 critical steps. So here we present the C implementation of a generic hashing function and the corresponding WebAssembly code for the given step. In step 1, the memory buffer is initialized using a precomputed hash state. Step 2 divides the message into blocks of a fixed size length and applies a compression function on each block. Step 3 checks if the remaining message size is less than the fixed length size, and if it is, the remaining bytes are copied over into a temporary buffer. Step 4 pads this temporary buffer with zeros and runs it through the compression function. And finally, step 5 returns the final hash state as the hashing result. MinerRay takes in standard WebAssembly, ASM.js WebAssembly, and JavaScript modules as input, and is composed of 3 main phases. The first phase, program language lifting, is responsible for building the IR by modeling the operations within these modules. The second phase uses the IR to build a control flow graph that models the entire program. And the third phase performs the hashing function Inference and also scans the web page for user consent events. The program language lifter is responsible for building the IR from the operations within the modules. One of the challenges we encountered was that ASM.js modules were captured as WebAssembly modules with non-standard opcodes. This is automatically performed by the Chromium browser and doesn't allow us to use WebAssembly tools on them. So in order to get around this, we develop a mapping that converts the non-standard opcodes into standard ones. Once these modules are standardized, we can then process them with the regular WebAssembly modules through our custom parser to build the IR. JavaScript modules can use the Esprima parser to build the IR. WebAssembly is based on a stack machine architecture. So in order to build the IR, we model the instructions based on their effects that they have on the stack. We keep track of variable assignments and operations that store into memory. The figure below shows the state of the stack as the WebAssembly code on the left is run. In the store instruction on line 4, an abstraction is created where it stores the value at the top of the stack into the location in the value stored in the value beneath it in the stack. We also need to model structured control flow constructs such as loop and if instructions. We do this by creating a new scope within these abstractions and then storing the subsequent instructions within this scope. Since hashing functions rely heavily on consecutive memory reads and writes, we also combine adjacent store abstractions into a single mem copy abstraction. Memcopy isn't a concept native to WebAssembly, but we include it because of its utility in identifying these hashing functions. Once the abstractions are defined, we then construct an independent control flow graph for each function. And then once these control flow graphs are defined, we combine them whenever there's a function call to create a control flow graph that models the entire program. We construct an algorithm to detect the critical steps of the hashing functions using the control flow graphs. In the first step, we iterate over all loop abstractions in the graph to find those with loop conditions that check for remaining blocks. For the loop conditions that match these conditions, we store some properties such as the block size and the remaining message pointer and carry them to be used in the next step. In the second step, we find conditional statements that follow the loops from the first step that check for a remaining partial message within a buffer and that contain an inner statement to copy the data into a new buffer. For the conditions matching these criteria, again, properties are stored and they're carried over into the next step. The third step checks for conditional statements that check if a buffer needs to be padded. We do this by seeing if the condition performs a comparison between the temporary buffer size and the block size used in the first step. We also check for a memcopy abstraction whose value can be traced down to a constant value, such as 0. For conditional statements that match this, again, properties are stored, and for a function that contains a result for each of these 3 steps, the function is added to the list of hashing function candidates. To perform the user consent inference, we inspect the web pages to see if they inform the user of mining. To do this, we scan the HTML document for strings like mining, CPU usage, and more. For the elements that match these criteria, we then search the JavaScript event handlers to see if the miner can start without the need for user actions. In the figure on the right, we see a pop-up of a miner asking for permission to mine. Inspecting the button's onClick function shows that it will only send the site key if the user allows permission. Tracing through the event handlers shows that the miner starting function, miner.work, is within the call path. To evaluate our technique, we test on the top 1.2 million websites from the Alexa top 10 million. We do this by calling the homepage and all available sublinks for 5 seconds. We use a modified Chromium browser to gather the WebAssembly and ASM.js modules by forcing it to dump out the WebAssembly module bytes to a file whenever they're processed. Using MinerRay, we found 901 unique domains containing cryptominers. 560 of these were detected on the landing page, and 341 were detected on subpages. In addition, we found that the majority of the websites lie within the top 500,000 sites. We identified 12 unique mining services that provided the crypto miners. The top service is the now-defunct CoinHive service, with CryptoLoot, the service that provides the variant Uplexa cryptocurrency, following closely behind. We compare our technique with existing detectors. MinerBlock and NoCoin are signature-based detectors that require predefined signatures for each cryptocurrency. Minesweeper counts bit operations such as XORs and left shifts within a WebAssembly module to recognize hashing functions. OutGuard uses a machine learning classifier to decide whether a page contains a cryptominer given collected runtime features, such as web workers, the number of WebSockets, the CPU usage time, and more. CM Tracker calculates the cumulative time spent on signature hash functions and by profiling stack signatures for predefined runtime behavior. The figure on the right shows that our tool performs better than the existing detectors, especially Minesweeper, which is prone to false alarms due to its simple operation counting. The user consent results show that of the 901 websites, only 16 websites informed the users of the background crypto mining. Of the 16, 13 automatically start mining, and only 3 explicitly ask for permission before mining. 7 of the 16 don't provide a way to disable the mining, and 15 out of the 16 don't provide a way to throttle the CPU usage. Generally, the performance overhead doesn't take up much resources. For the average file size processed, which is around 447 kilobytes, the total memory usage was around 37.23 megabytes. Graph construction time took around 428 milliseconds, and the graph scanning time took 1.4 seconds. MinerRay faces some limitations that we will leave as future work to address. These include limitations in the data collection methodology, resilience to obfuscation techniques, and the generality of the technique. For our data collection methodology, we use web crawlers to visit the homepage and all available subpages for 5 seconds. It's possible that some cryptominers may only be triggered by certain user events or after long idling periods. By incorporating more effective web crawling techniques, we could potentially identify more cryptominers. Cryptominers can be obfuscating using some obfuscating techniques. For simple techniques such as opaque predicates, changing variable names, or injecting dummy code, MinerRay is still able to determine the underlying hashing semantics. For more advanced techniques that would encode or encrypt an entire program, these may break MinerRay detection. Our technique assumes that the cryptographic hash functions used to perform the mining rely on block ciphers. Since this applies to most hash functions, the technique is general. However, to support more languages, the IR would need to be extended to be able to model the hashing semantics within the new language. Our technique is most closely related to existing detection work based on URL blacklisting, CPU usage profiling, behavioral analysis, machine learning techniques, code analysis, and techniques that identify cryptographic functions. In conclusion, we present MinerRay, an effective technique to detect diverse cryptominers in in-browser cryptomining. Our technique relies on an IR abstraction to model the hashing semantics necessary for cryptomining. We evaluated our tool on 1.2 million websites and detected 901 mining sites, allowing our tool to perform comparably or better than existing detection tools. Thank you for watching, and we invite you to ask any questions.
Okay, thank you very much for the talk. Are there any questions? So let me ask a question. Can you envision, I mean, this is a bit specific to the cryptojacking issue, because you're looking for specific kinds of data manipulations. Can you imagine any other kind of problems where a similar technique would be useful?
The generic IR could be extended to find more kinds of data manipulation areas, but the actual detection algorithm is pretty tuned to finding hashing functions. So the IR could be used in new domains, but then it would be on the user to kind of learn the IR and then model whichever pattern that they're trying to identify with the IR.
Are there any other problems that have a similar kind of very fixed pattern like this one does?
I'm not aware of any off the top of my head.
Okay. Okay, I mean, it seems very practical for what it does, so it's very nice.